We're going to continue our discussion of Chapter 5, the physical examination of urine. Urine concentration is a really important characteristic. This allows us to determine the concentrating ability of the kidneys, and it refers to the amount of solutes present in a volume of water excreted. Urine normally consists of 94% water and 6% solutes. Solutes, these are things that are dissolved in your urine, vary with the patient's diet, physical activity, and health. Dilute urine has fewer solute particles per volume of urine. Concentrated has more solute particles. The color of a urine is a crude indicator of its concentration. The darker the yellow, the more concentrated the urine is. When you get up in the morning and you first use the restroom, you'll notice that your urine is very dark. That's because normally we don't get up in the middle of the night to urinate, and so it becomes more and more concentrated over time. Urine concentration is expressed as specific gravity or osmolality. In healthy people, there's a really good correlation between the urine specific gravity and the osmolality. With the disease process, this relationship may not exist. Procedures for specific gravity and osmolality differ with respect to the instrumentation used, the complexity of the procedure performed, and the time to perform the procedure. Specific gravity is used to rapidly assess concentration. Osmolality is used when more accurate and specific information is required. Specific gravity is an expression of the concentration of urine in terms of density. This is the mass of solutes present per volume of solution. The ratio of urine density to density of an equal volume of pure water under standard conditions. Both the number of solute particles and molecular size affect specific gravity. The greater the density of the urine, the greater the specific gravity. It is physically impossible to excrete pure water. There will always be solutes present in your urine, even when the kidneys are going down. The lowest possible urine specific gravity is about 1.002, and the highest is about 1.040. Methods of measurement of specific gravity are categorized as direct or indirect. The molecular size of the solutes does not affect the indirect specific gravity measurements to the same degree as direct methods. Direct specific gravity determines the actual or true density of urine. All solutes are detected and measured, including those that are always in the urine, such as urea and electrolytes. Those present as a result of disease, glucose, and protein. For iatrogenic reasons, radiographic material, again, this is used to enhance X-rays and is injected intravenously. If radiographic material has been used, it's best to collect a sample at least 8 hours after the procedure. High molecular weight solutes do not reflect the renal concentrating ability of the kidneys. It's present because of abnormal processes unrelated to the processing abilities. Glucose and protein will elevate the specific gravity. Indirect methods such as refractometry and reagent strip chemical methods are the most common methods used to measure specific gravity in urine samples. Refractometry is an indirect method based on the refractive index of light. When light beam passes from the air into a solution at an angle, it refracts and slows the direction of the beam. The ratio of the light refraction and two different media is called the refractive index. As the number of solutes increases, the light velocity decreases, and that makes sense because it's more difficult for the light to pass through. And as a result, the light angle will decrease. Here's a schematic diagram that illustrates the refraction, or otherwise known as bending, of the light as it passes from one medium to another of differing density. The velocity of the light beam also changes. Here's a picture of a refractometer. These are still frequently used in the clinical laboratory. Here's the eyepiece. It's similar to the eyepiece on a microscope. Here's where a couple of drops of urine are placed, and then the magic happens, where the light is refracted and we get a measurement. Three factors affect the refractive index of a solution in refractometry: the wavelength of light used, the temperature of the solution, and the concentration of the solution. Temperature and concentration produce changes in the density of the solution. Refractometry measures all solutes present, including protein and glucose. Within the refractometer is a prism, a liquid compensator, and a chamber cover, which work together to direct a single wavelength of light onto the calibrated scale. The most common wavelength used is 589 nanometers. Calibration is checked daily using distilled water, which has a specific gravity of 1.000. So again, anytime we're going to use a piece of equipment, there are certain steps that need to be taken to ensure the accuracy of the results. This is the first step taken every day, and it's recorded. Also, one or two additional solutions known as calibrators of known concentration are used to ensure calibration range across the possible specific gravity values. They may use one that has a low specific gravity and one that has a high specific gravity, and the results must match the manufacturer's, or that instrument cannot be used. Some of the advantages of refractometry are the small sample size. Only 1 to 2 drops of sample are needed. It automatically compensates for temperatures between 15 to 38 degrees. In the viewing field, there's a distinct edge between the light and the dark areas, making reading the specific gravity scale very easy. So this is the viewing field. When you look through the eyepiece, you'll see this, and this has a solution that's been added. The darkness meets the light, and where they come together, you read off the scale. This is urine specific gravity, and this one reads 1.029. This is for serum or plasma, and this is for refraction. For urines, we always go by this scale. So again, if you see this picture on a test, I want you to have the ability to be able to read off of it and tell me the specific gravity. The reagent strip method is an indirect colorimetric estimation of urine density based on the amount of The reagent strip method to measure urine-specific gravity is an indirect colorimetric, meaning a color will be produced, estimation of urine density based on the amount of ionic or charged solutes present. These are sodium, potassium, chloride, and ammonium. Non-ionic solutes such as glucose, urea, protein, or radiographic media are not measured. This method determines ion-specific gravity. Remember, in refractometry, these substances did affect the specific gravity. Healthy individuals' ability of their kidneys to selectively reabsorb and secrete ionic and water determine the concentration or density of the urine excreted. So remember, your kidneys are excellent at maintaining homeostasis. They will excrete substances that are toxic to the body and then retain those substances that benefit the body. The excretion of urea, glucose, protein, or radiographic media does not reflect the state of renal function. The presence of glucose in the urine usually indicates a metabolic disorder such as diabetes mellitus. The presence of protein in a urine is not good and indicates a renal condition as a change in the glomerular filtration barrier. Protein should never cross that barrier, and if so, it may indicate conditions such as glomerulonephritis or nephrotic syndrome. This is the only method that eliminates the effect of non-ionic large molecular weight solutes on specific gravity, such as radiographic media and of course the protein and the glucose. It may not represent the true density of the urine, but it does reflect renal concentrating ability to handle solutes in water. You've used reagent strips to chemically examine urine, and for specific gravity, the reagent strip pad is impregnated with polyelectrolyte and a pH indicator, bromothymol blue, at an alkaline pH. When the strip is immersed in urine, protons are released from the polyelectrolyte in proportion to the ionic concentration present in the urine. The released protons change the pH of the test pad, and this results in a color change of the pad. The more concentrated the urine, the more intense the color. Most accurate results are obtained with the urine pH is 7.0 to 7.5. More acid urines may cause falsely increased specific gravity results. More alkaline urine causes falsely decreased results. With any laboratory procedure, it's imperative to know the limitations of each method. You may do a kit test. You may do other types of tests. The first thing you always do is read that reagent package insert. You not only want to know how to correctly perform the test, but you need to know what may affect the test and produce inaccurate results. You need to recognize that it's physiologically impossible to have results which are outside 1.002 and 1.040 for urine-specific gravities. If you get a value outside these ranges, something is wrong and you need to repeat it. An abnormally high specific gravity, greater than 1.040 by refractometry, but a normal specific gravity by reagent strips, should consider radiographic contrast media or other large molecular weight solutes. Again, the refractometer measures everything, including glucose, protein, and those radiographic materials. The reagent pad does not detect those. Large quantities of glucose and protein falsely increase the specific gravity by refractometry, but does not affect the reagent strip. So you just when working in the laboratory, it's imperative to know the limitations of each method of specific gravity. And in general, it's important to know the limitations of any procedure that you perform. The first thing you do when you learn a new procedure is you will learn the step-by-step instructions to perform it, but you also need to know the limitations, what are things that may cause inaccurate results, false positives or false negatives. Recognize that it's physiologically impossible to have urine results which are outside 1.002 to 1.040. If you get this type of result, you need to investigate as to the cause. An abnormally high specific gravity value of greater than 1.040 by refractometry, but a normal specific gravity by the reagent strip, should consider the radiographic contrast media or other large molecular weight solutes should be suspected. Also remember that large quantities of glucose and protein falsely increase specific gravity by refractometry, but does not affect the reagent strip specific gravity. Osmolality is the concentration of a solution expressed in terms of osmoles of solute particles per kilogram of water. Molecular weight does not affect osmolality, and it's also not affected by temperature. Milliosmoles are the units that are most often used for convenience due to the low osmolality of most biological solutions. The reference ranges for osmolality for urine is 275 to 900 milliosmoles per kilogram, and for serum is 275 to 300 milliosmoles per kilogram. Kidneys excrete unwanted solutes in the volume of water that the body does not need. Urine osmolality can vary greatly depending upon diet, fluid intake, and physical activity. Serum osmolality remains relatively constant, and you can see by the numbers 275 to 300 is the normal range for a serum osmolality. The principal uses of osmolality are to evaluate renal concentrating ability of the kidneys, to monitor renal disease once it has been diagnosed, to monitor fluid and electrolyte balance, and differentially diagnose the cause of polyuria. So we get an abnormal specific gravity. This may be a test the physicians will order in order to investigate causes as well as monitor treatments and therapies. It's determined by measuring a colligative property of solutions such as freezing point depression or vapor pressure depression. Freezing point osmometry has the ability to detect the presence of volatile solutes, and these are solutes that once they're exposed to the air can dissipate very rapidly. It also gives accurate results even with lipemic samples. Lipemic samples, if you will recall from phlebotomy, These are samples that have a lot of fat in them. Pure water freezes at 0 degrees centigrade, and when you add 1 osmol of solute particles to 1 kilogram of pure water, it decreases the freezing point by 1.86. So the more solutes that are present, the lower the freezing point, and this relationship is constant. There are 4 principal components to freezing point osmometry. The mechanism to supercool the sample slowly to about -7 degrees centigrade. A thermistor to monitor the temperature of the sample. It has to have a method to initiate freezing induced by seeding, and they usually use a little wire. And a direct readout display when the freezing point is reached. The osmometer will read the freezing point of the sample and converts to a direct readout in milliosmoles. This can use either serum or urine. Vapor pressure osmometry is not as common as freezing point osmometry and is typically done in reference laboratories. It indirectly measures the decrease in vapor pressure caused by solutes in a sample by measuring a decrease in the dew point temperature. It utilizes a small sample size, but it is unable to measure volatile solutes, thus limiting its clinical applicability relative to freezing point depression methods. In summary, both osmolality and specific gravity are expressions of urine concentration. Heavy molecules such as glucose, protein, and radiographic media significantly affect refractometer-specific gravity measurements, but do not affect osmolality or reagent strip measurements. Because all solutes contribute equally to osmolality regardless of molecular size, osmolality is considered to be more accurate in assessing solute concentration in serum and urine. Be sure to review Table 5.6 on page 78 for test methods and the limitations of each. The last physical characteristic of urine we're going to talk about is volume. Normally, you will excrete 600 to 1800 milliliters of urine per day. Urine samples are not routinely assessed for volume. Volume is only monitored for very specific tests, such as a 24-hour urine. The amount of solutes excreted increases as water required to excrete them increases. You need to memorize each of these terms which describe urine excretion. Nocturia, excretion of greater than 500 mL at night. Isocenthuria is the inability of kidneys to change specific gravity of plasma ultrafiltrate, which is 1.010. This reflects damage to the kidney's tubules or the renal medulla. Polyuria, excretion of greater than 3 liters per day. Oliguria, excretion of less than 400 milliliters per day. And anuria, the complete lack of urine excretion. And I don't know if you've taken med terms, but urea always refers to urine. Table 5.7 summarizes urine volume terms and the clinical correlations. This ends the presentation for Chapter 5. Again, you should have been writing down any questions you have, and after reviewing your textbook and after reviewing this presentation, if they're still not answered, please provide those to your instructor when you go to class.